What if I told you that our most basic, common sense view of reality is just plain wrong? This idea that things are separate and have definite properties? Well, it turns out that one single experiment completely shattered that notion. This is the story of the ultimate test for our universe. It all starts with a puzzle that even stumped Albert Einstein. Quantum mechanics predicted something so bizarre, he famously called it spooky action at a distance. Imagine two particles, mysteriously linked. Whatever happens to one of them, instantly, and I mean instantly, faster than light, affects the other, even if they're on opposite sides of the galaxy. To Einstein, this wasn't science. It was just impossible. And right there, the stage was set for one of the greatest scientific debates in history. In one corner, you have Einstein's intuition, the logical, predictable world we all experience every day. And in the other, you have the truly weird predictions of the quantum world. This wasn't just some abstract physics argument. This was a fight for the very soul of reality itself. Okay, so let's break this down. Einstein's view is called local realism. It's based on two simple ideas. First, locality. An object can only be influenced by what's right next to it. Nothing travels faster than light. Simple. Second, realism. Things have definite properties even when we're not looking. Like he used to say, the moon is still there even if nobody is looking at it. But the quantum view, it was totally radical. It proposed entanglement, where linked particles act as a single system, instantly, no matter the distance. And it claimed that a particle's properties are fundamentally uncertain. They're not even real until they're measured. Now, for almost half a century, this was just an argument on paper. There was no way to prove who was right. You either sided with Einstein's common sense or the weird quantum math. But that all changed when one physicist decided to stop arguing and actually design an experiment to force the universe to finally show its hand. The journey to this verdict was a real saga. It started way back in 1935, when Einstein and his colleagues published the EPR paradox, which was their ultimate argument for why quantum theory had to be incomplete. For decades, the debate was just stuck. But then in 1964, a physicist named John Bell came up with a genius mathematical theorem that changed everything. It made this philosophical argument testable. And that brings us to 1982, when Alain Aspect in France finally ran the experiment designed to answer the question, once and for all. Okay, what's really fascinating here is just how clever the experimental design was. Here's how it worked. First, a source creates pairs of entangled photons. Second, those photons get fired off in opposite directions. Third, the settings on the detectors at each end are changed randomly. But here's the real kicker, step 4. That change happens while the photons are still in flight, so fast that no information, not even a light-speed signal, could possibly travel from one side to the other. This brilliant move closed the last loophole, making sure the particles couldn't be conspiring behind the scenes. So, this was the moment of truth. The experiment was running. The data started to pour in. Would the correlations between these particles obey the limits predicted by Einstein's common sense, or would they dance to the spooky tune of quantum mechanics? The results came in, and they were completely undeniable. The world of physics and our entire understanding of reality was about to change forever. Common sense lost, the results violated something called Bell's inequality. You can think of it as a mathematical speed limit for a common sense reality. Aspect's experiment showed that the particles were far more coordinated than that speed limit allowed, and they matched the quantum predictions perfectly. Einstein's spooky action wasn't a flaw in the theory. It was a fundamental fact of our universe. The ghostly connection was real. So here's the crucial takeaway. This result forces us to make a choice. We have to give up one of our deepest beliefs about the world. Option 1, we ditch locality. We accept that the universe is fundamentally interconnected, and that influences can happen instantly across vast distances. Or, option 2, we ditch realism. We accept that the physical world has no definite properties until we observe it, that the very act of measurement creates reality. Either way you slice it, our classical worldview is shattered. But this discovery wasn't just about tearing down old ideas. It was about building a new future. Proving that entanglement was real handed us the keys to a whole new kind of technology, stuff that was previously just science fiction. This spooky phenomenon unlocked a brand new toolkit. We're talking about quantum cryptography. Imagine unhackable communication, secured not by a password, but by the laws of physics themselves. Then there's quantum computing, machines that could potentially solve problems that would take our best current computers billions of years. And this is paving the way for things like quantum teleportation and an ultra-secure quantum internet. And here's a brilliant illustration of how it works. In quantum cryptography, two users, let's call them Alice and Bob, share entangled particles. If an eavesdropper, Eve, tries to listen in and measure a particle, her very action instantly disturbs that fragile quantum connection. Alice and Bob immediately know someone is there. It's like having a security system that's baked into the very physics of the message itself. And in 2022, the world gave this revolutionary work its highest honor. 40 years after his experiment, Alain Aspect, along with John Clauser and Anton Zeilinger, received the Nobel Prize in Physics for turning this spooky paradox into the foundation of quantum information science. The technology is incredible, no doubt, but the philosophical implications? They might go even deeper. If the fundamental rules of reality aren't what we thought they were, what does that mean for us? I mean, just think about this for a second. This experiment proves that at the deepest level, the universe isn't a collection of separate things. It's a fundamentally interconnected web. If two photons can be part of the same single system across the cosmos, what does that say about our own feeling of being separate individuals, isolated from each other and from the world around us? Or consider the other option. If reality has no definite form until it's observed, that places a strange and powerful role on the act of observation itself. It suggests that consciousness, the act of looking, might not be a passive act at all, but an active participation in bringing reality into being. And in the end, we're left with this ultimate question. The experiment that shook reality didn't just give us answers, it opened up even deeper mysteries about our place in the cosmos. Are we just passively watching a cosmic movie that's already been written? Or are we, with every observation we make, co-creating reality itself? The answer? Well, that might still be waiting for us to see.